So, okay. So what we have done in StatMech so far is two parts. The part one was really fundamentals. We started with things like equal a priori probabilities and ergodic hypothesis and things like that. We worked through our ensembles and we derived the probability of microstate in every ensemble, right? And the whole idea was an ensemble tells you what do you know about the environment, what do you know about the atmosphere, and that tells you probability of the microstates. In part two, we did some applications to non-interacting systems. And this might have escaped your attention that things were non-interacting. I want to emphasize that today because now we are going to start part three, which is application to interacting systems, which is really all of chemistry. Even the non-interacting system approximation works out to be quite nice, works out to be quite powerful, which is amazing, but it is an approximation. So what do I mean by non-interacting system? And as we get into part three, let's remind ourselves of what do I mean by that. So let's say I have a box. And let's say in this box, I have Didi. He's very happy. He has a cap today. And let's say that there is Disha. She's not happy. She has to decide grad school soon. And it's exploding her head. Sorry, not DW, DS. And non-interacting means they are not talking to each other, right? They are not aware of each other's existence. If I approximate both of these as ideal gases, if Didi, you were an ideal gas particle, what would you be doing in this box?
Spreading out.
Bouncing around like a maniac, like mad. Maybe you do that already. I don't know. I haven't seen you bounce around, So you will be bouncing around back and forth. So that's what Disha will also be doing. Every once in a while, there will be elastic collision. It will be fully elastic, and they will just bounce back and things like that. And you could put in as many particles as you wish in this, right? It will work that way. So in this case, what is the total energy of the system? It's zero, right? The total potential energy of the system is zero. The only thing you have is kinetic energy, right? Kinetic energy is not equal to zero, and that's what they're moving under. Now, what we did was a bit more complicated than this in part two. Didi and Disha were still independent of each other, but they were working in some energy well, right? We used quantum harmonic oscillator and things like that. In that case, for example, when we did quantum harmonic oscillator, Didi had his energy levels, Disha was following the same energy levels, right? And depending on the temperature we had, they could be in ground state, they could be in excited state, things like that. We did all of that. So in that case, K was again not equal to zero, and U was also not equal to zero, right? But notice that our U here, U for the system, was going to every particle, I is equal to 1 to n. And we had the potential energy for that one particle at a time, right? The potential energy is, in that case, was additive among one body terms, right? Disha was experiencing some potential energy, Didi was experiencing some potential energy. There was no interaction between them, right? That's how we tackled the problem. We went one step further. We went from distinguishable to indistinguishable. So if I am the observer, I am the one doing the math. Let's say I don't care whether it's Disha or Didi. I do, but let's say I don't, right? So how would I work with that? In that case, what I did was to take Q independent from calculating the Q or the Q indistinguishable. I calculated the Q distinguishable for each particle, right? Which was the same. I took to the power n, and then what did I do? I divided by n factorial. And I showed how this is a good approximation. This was good approximation in high T and low density limit, right? And this is something which will come up, which should have come up in your homework, in the recent homework that you're going to submit soon. You have to be careful about using the n factorial approximation. So in other words, this is the same as, this condition is it's the same thing as saying when number of states accessible to the system is much more than the number of particles in the system. And sometimes you can get contradictory things here. You would be like, well, aren't you talking about large n and thermodynamic limit? So what does it mean to say that number of particles is very small? No, number of particles is large on its own for thermodynamics to be applicable. But the number of states is way larger. It's even more, right? So we had situations like this where we had just a lot of states, right? And few particles, maybe one particle here, one particle here, one particle here, one particle here. So the probability of finding two particles in the same state went to zero. It was not exactly zero, but it went to zero, right? And we saw that with this approximation, both Einstein and Fermi-Dirac achieve the approach the classical approximation with this n factorial term, right? In that limit. So be careful in the homework, because if you don't have too many states, if you have a small number of states and similar number of particles, then n factorial is not going to work. You will actually have to think very carefully. Maybe you'll have to go through canonical partition motion and think very, very carefully. Any questions about this? So that was n non-interacting particles. They are experiencing their own potential energy, but they are not talking to each other. What we are going to do next is interacting systems. Chandler calls it as classical fluids. This is pretty much all of chemistry. Polymers, proteins, RNA, DNA, water, anything that you can think of falls in this category. Here, the particles talk to each other, and that makes life very complicated. So let's go to my box again. Let's again use our involuntary models, Didi and Disha. So Disha is over here. She's not exactly pleased. Didi is over here. He's very happy. He has a cap. You have to be accurate. So now, and let's throw one more person in the mix. Ami, what are your initials? Disha, Sanwal, Didi. You're just Didi. AB. Are you happy or sad or pleased? You're happy. So he has a big grin. Okay, good. This is important. No. We make you very happy. Okay, he's very happy. So now they are all interacting with each other, right? It's like, get out of my way. I don't like you, whatever. Or I like you. I want to sit next to you, whatever. There's some sort of interaction going on. So if they were not interacting with each other, if they were ideal gas particles, what could we have said about the pressure volume dependence of such a system? If they were ideal, it would have been PV is equal to nRT, right? PV is equal to nRT means that not only they are not interacting, they don't even experience any one body potential term, right? They are just completely free. In the last homework, there is a problem where you will derive that for fermions, for example, this is not true. For fermions, PV is more than nRT. For bosons, PV is less than nRT, right? So now we are going to think of a more complicated setup. So ideal gas means U is equal to 0. There is no potential energy, right? General case, U is not equal to 0. You could have some attractive potential between two particles, or you could have some repulsive potential, or you could have a potential which is a combination of both of them, right? So the simplest way to think about the potential is to plot the potential as a function of the interparticle distance, okay? U as a function of R. So if I was to plot U as a function of R, and these two particles are attractive, they don't like to be infinitely apart from each other, they like to get closer. How would U of R versus R look? Should it be lower at R is equal to 0 or higher? Huh?
Higher.
Attractive.
There's no repulsive force at all.
If it's attractive, it should look like this. The energy goes down as you come closer. Okay? So this is attractive. There is no repulsive force at all. This is repulsive. It's like, don't get in my space. As R tends to 0, it blows up, right? In reality, potentials are a sum of these two. A most famous example is a Lennard-Jones potential, where you have a sum of these two, and it looks something like this. So if you want to have bond formation, you will have some sort of an equilibrium length where atoms like to get close, and you cannot pack them any closer, right? And if you move them apart, then further apart than that, they try to come closer. If you pack them further in, they say like, go away, okay? So that's these type of things. That's a simple example of non-ideal gas potential, right? And there could be very complicated mathematical terms. In fact, when I write, if I was to say that U of Rn, by Rn, I mean the full potential energy of the n particle system. Okay, here I drew 2, but let's say this was particle number 1, this was particle number 2, and there's a bunch of them. There is a particle number n. So here, what am I saying? I'm saying U of Rn is equal to summation of every ij and an interaction that depends on the distance between particle I and particle j, right? That's the type of interaction. These are what is known as a pair interaction. Most things in chemistry do not have a pair interaction. Water is the classic example. If you just had pair interaction, water would not be bent. Water has 109 degrees angle. For most things, you also need to care about things like the angle between three things, right? You have to introduce what is known as a three-body term, right? A pair interaction. This is a two-body term. You could also have three-body terms, which depends on I, J, K, three atoms at the same time, right? You could have what comes after an angle in geometry. For biology, it turns out even angle is not sufficient. You have to care about torsions. When you have a protein, you have to look at the torsion of the angle, right? Then you have to worry about four-body terms, and it can keep getting more and more complicated. In what's going to follow next, we will deal a little bit with pair interactions. We are not going to go beyond pair interactions. It's already quite useful for us. But the problem that I'm trying to set up is, if I gave you a system where I know something about the pair interactions or something about the potential energy, how can I go from that to the thermodynamics of the problem? So when U of R, when U was equal to 0 for everything, it was completely ideal gas. You know, the equation of state is PV is equal to nRT. But what would be the equation of state for one of these things? That's the question we want to answer. Vice versa. So if you're doing computer simulations, it's easy to measure this U of R. In my field currently, people are going crazy over what is known as machine learned interactive potentials, MLIP. It's like even the tech bros are very excited about it. There are venture companies which are raising $100 million to fit these type of things. It's ridiculous. I'm like, really? Fine, good for you. The idea there is you do quantum mechanics, you use a lot of GPUs, and you fit this U of R. And more complicated terms, they are going to fit everything. What they do is to express all these terms as neural networks, right? So it becomes very accurate. And they think if we can do this, then they can go and calculate all the thermodynamics. In reality, the story is opposite. You go and measure your equation of state. You went and synthesized this fancy chemical in lab, and you don't know what it is, right? What you do, you beat it. You beat it and see how much does the volume change, right? You heat it and you see how much does the volume change, right? That's what it is. You beat and heat things, and you measure the volume, you measure all sorts of responses, you measure equation of state, and then you try to infer what was the interaction between these things, right? Is it really funky quantum mechanics? What's going on, right? But the general problem we are trying to solve is, how do I go from a complicated n-body interaction potential energy to the thermodynamics of the system? And it's not easy as you might think, because the thermodynamic of the system, in principle, if you know the potential energy, then writing down the partition function is easy, right? What is the partition function? Partition function will be Q, every single particle, dr1, dr2, dr3, drn, e to the power minus beta u of rn, right? If this u of rn was additive, it dependent on every single particle separately, then this, if u of rn was u of r1 plus u of r2 plus dot dot dot, then q would be simpler. It would be integral dr1 e to the power minus beta u r1 integral dr2 e to the power minus beta u r2 dot dot dot, right? So here on the top, q is a 3n dimensional integral, and on the bottom you have written it as a product of 3-dimensional integrals. 3-dimensional integrals are hard, but not as bad as 3n dimensional integrals, right? So this q can be calculated for such simple potentials. But if you did not have just u of r1 and u of r2, if you had complicated terms, it's going to be really, really hard to do that, right? So getting the partition function is really hard. So we want to develop approximations for this, and we want to develop theories, and it turns out it works quite nicely. So yeah.
So if you can break down a potential into just pairwise interaction terms, would that let you separate things out into?
That's what we are going to do in the next 4 classes. It's still very hard.
Okay.
That will lead to potential of mean force and things like that. That's the case we are going to focus on. That's something we can do through algebra. For anything more complicated, you have to use computer simulations, but that's exactly what we're going to do. Okay. So in order to describe such a system, and as I mentioned, the language changes a little between part 2 of this course and part 3 of the course, right? So we are still doing StatMech, but we are going to use different type of language to describe the system. And let's become a bit more rigorous now. So I'm going to just change page. What we are going to do next, in order to describe such an interacting system, I have to introduce the concept of distribution functions. What do I mean by distribution function? Let's draw my axis. There is everything exists in 3D world in what we are doing here, x, y, and z. Okay. In these x, y, z coordinate, let's say the vector for particle number 1 is over here, and the vector for particle number 2 is over here, right? They exist somewhere in space, in 3-dimensional space. The simplest distribution function I'm going to introduce for this system is called, and be careful now with the superscripts and things like that, P of 1, superscript 1, that depends on the vector R1. So this is the vector R1, this is the vector R2. And again, if this is all confusing, I'm very closely following Chandler chapter 7. Not in the exact order, I am trying to give some intuition before I go into more of the math. So P1 of R1 is the single particle distribution function. It's defined as the single particle distribution function. And this is the probability of finding particle 1 at the vector r1, right? The thing is, we are talking about interacting systems. So we have to worry about not just one particle at a time. We have to worry about how are these two particles going to behave with respect to each other, right? So we have to go one step further in the hierarchy. And we have to talk about the two particle distribution function. Now I'm going to use a superscript of 2. This one is going to depend on two vectors, r1 and r2. This is now probability of finding particle 1 at r1 and particle 2 at r2. And notice I'm being very careful with the identity of the particles. I'm not saying this is the probability of finding two particles, one at r1 and one at r2. Okay, I'm not masking out Disha and Didi. I want to know what is the probability of finding Disha here and Didi here, which is not the same as swapping them, right? In a bit, we are going to look at that other probability. But for now, these are distinguishable, okay? You could go further, right? You could write down a similar three-particle distribution function. R1, R2, R3, dot, dot, dot. The world is your oyster, right? You can keep writing as many particle distribution functions as you wish. The question now is, how does the two particle, and these two particle systems are, these are two particles out of a total n. The whole system has n particles, okay? And the potential energy of the total system is r to the power n. It's some complicated, super complicated function. It's a deep neural network. I don't know what it is. That depends on very complicated way on positions of every single particle and how they are with respect to each other, okay? So what I want to do is to write down, and most of this remaining class, we are going to focus on P2 and P1. We are not really going to talk about P3. And the reason we will focus on P2 is because it connects to scattering, it connects to XRD and neutron scattering and things like that. So it's very, very useful for a variety of reasons. So just to remind you, potential energy of n particle system is U of r to the power n, okay? Given this information, what can you tell me about P1 of R1? What will be the relation between P1 of R1 and capital U of r to the power n? How would I get this thing from this thing? Any ideas? Right.
I want to say it's somehow it's related to the partition function Q. That's like the integral over.
Yeah, it's related to the integral. So let's think of it intuitively. Again, I will focus on Didi. So this is me trying to calculate the probability of observing Didi in this chair, right? Averaging over whatever else you all are going to do. So you all might be doing a ballet, jumping around, fighting each other, I don't care. Whatever you can do. This is going to be an integral that averages out everything else in the system except Didi, right? Which is kind of how we live, right? We all care only about ourselves. We really don't care about anything else. This is just saying I'm the center of my universe. I don't care about anyone else. I'm just going to average it out. But this average won't do. I have to look at the Boltzmann weight of the average, right? And what is the Boltzmann weight? That is e to the power minus beta u of Rn. And just to be clear, when I say Rn, Rn is a shortcut for a very complicated vector, okay? I don't want to be writing this all the time. So when I use subscript, subscript is equal to particle number, okay? And superscript is really showing system size, okay? Does this make sense? Let's call this equation number 1. Okay?
Isn't that the partition function?
No. I am not integrating over R1.
Okay, I missed that.
If you took the partition function, then Didi will also be washed out.
Okay.
We want to keep Didi's variable R1 alive. We want to integrate out everything else, R2, R3, Rn, okay?
Gotcha. Yeah, I just missed that.
Yeah. Now, let's go from here and talk about P2. When I'm interested in finding Didi at R1 and Disha at R2, now what will I do? It will be the same integral, but I won't integrate out R2. I will keep R2 also as a variable, okay? So this will be integral dr3, dr4, drn e to the power minus beta u of Rn, okay? This is the two particle distribution function. Let's call this equation number 2. Notice that I'm just talking about the probability of finding them at a certain position. I'm not talking about their momentum. And to really describe this system, I also need to, that the full partition function of this system will involve not just that position, but just he's sitting here does not mean that he's not moving. It does not tell me anything about what he's doing over there, right? So there is the momentum part, which tends to be easy. I'm going to consider the momentum part towards the end of this class, and then we will forget about it because it just becomes a constant. It integrates out, but I still want to show you what it is. It relates to something known as the thermal wavelength. For now, we are just thinking about potentials. Okay, if you wanted to do a 3-body distribution function, 3-particle distribution function, you will not integrate out R3, you will start from R4, R5, R6, go on, and from there, okay? So,
But we're also assuming that the potential energy has nothing to do, it is decoupled from the kinetic energy.
oh, absolutely, absolutely. We have assumed that total energy H, the total Hamiltonian, is a sum of a kinetic energy that depends on the n particle momentum plus a potential energy that depends on the n particles position, okay? Let's finish out the momentum part. And then I will come back to equation 2 and proceed from there, okay? So if I really wanted to write down the partition function for this system, Q of beta n volume, the canonical partition function, I would have to not just integrate over position, I would have to integrate over momentum also, right? So the true partition function for the system would be integral over all momentum, integral over all position of e to the power minus beta h, right? Where h comes from equation 3. What would this be? This we can separate out. This would be integral d. Such a Hamiltonian has a name. This is known as a separable Hamiltonian. It can be split into kinetic plus potential energy. Most of these systems in chemistry tend to have separable Hamiltonians, but if you have a magnetic field and things like that, then life becomes crazy. Then position becomes coupled to the velocity. And then don't come to me for help. So dPn e to the power minus beta kinetic energy that depends on Pn multiplied by drn e to the power minus beta u of Rn. Let's write it down even more explicitly. This is dP1, dP2, dPn. Now it's an n-dimensional integral. Actually, it's a 3 n-dimensional integral, right? E to the power minus beta k p of n multiplied by another 3 n-dimensional integral dr1, dr2, drn e to the power minus beta u of r to the power n. I'm going to stop here for a moment, and I want you to pay attention to these two terms. What is the difference between these two terms? What's the difference between the right side of equation 1 and this one? In right side of equation 1, I have not integrated out R1, right? It still depends on R1. So that's not the partition function. It looks like the partition function, but notice it is missing dr1. In the bottom one, I actually have full dr1. Let's call this equation 4. Wait for just a moment. Okay, I'll move to the next page. So our partition function, and I will write down the last equation again. So our partition function is Q equal to dP1, dP2, dPn e to the power minus beta kinetic energy that depends on all n momentum multiplied by position vectors dr1, dr2, drn e to the power minus beta u that depends on all positions rn. Okay. I'm going to come back to this in great detail as we resume our discussion after equation 2. So for now, what I want to do is to focus only on the momentum part of the integral and show to you that it is actually quite simple and it becomes a constant number. And I will give you some do-it-yourself exercise for today, a couple of them. Okay, it's just a caution. Why is that so easy? So what is kinetic energy for a system? For an n-particle system, we don't know about the potential energy. It depends on one body, two body, three body, neural network, Wall Street, tech bros, San Francisco, I don't know, whatever is there, right? Machine learning, interatomic potentials, Army's advisors might be working on things like that. Coupled cluster calculation, I don't know, some whatever garbage you want to say, right? Something super complicated. Kinetic energy is, however, very simple. What is the kinetic energy of n particles? What is the kinetic energy of one particle? Ami. P square over 2m. If I throw another particle, how does the kinetic energy change? It just adds up, right? It's additive. Kinetic energy does not have multiplicative terms. Kinetic energy is always separable into the one part. Even though it's an interacting system, the kinetic energy is always going to be a sum of individual kinetic energies. This is, if you think about it, this is kind of amazing that it turns out to be that way, right? Even for this complicated system, the kinetic energy will be P1 square by 2m plus P2 square by 2m plus dot 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 plus Pn square by 2m. Does not matter what is the potential energy. Unless we are getting into relativity, which we are not, this is simple, okay? In other words, I can write down my Hamiltonian for a general system as I is equal to 1 to n pi square by 2m plus some complicated machine learned force field or whatever it is that depends on all n particle positions, right? And we will deal with that later. So let's call this as equation number 5 and this one as equation number 6. So if we put equation number 5 and 4 and we will focus, I want to give this a name. I want to call this as Greek letter phi that depends on the n particle momentums. And this one I want to call capital P that depends on all particles Rn. If you remember the nomenclature that we were using earlier, but if we had to be really pedantic, we could have called it P0, right? Because we have integrated out everything. Notice when we did P1, we integrated out n-1 things. When we did P2, we integrated out n-2 things. So if you really wanted to be pedantic, this is P0, right? It does not really, I mean, yeah, but well, I should be careful. This is not, it's not P because it's integrated out, right? So it's the partition function. Let me not call it P. This is a better way. What symbol should I use for it? Sorry about that. I'm not going to call it phi. You have to cut it out. This is going to be QP and this is going to be QR. Let's just call it that, right? It's not the probability because we have integrated out everything. So I want to focus on QP, okay? And I want to use equation 5 for QP. So what is QP? QP is, it is the momentum partition function, right? So we are looking at all momentum variables, dP1, dP2, dPn, and we have a complicated kinetic energy in the exponential. Turns out kinetic energy is not that complicated. It's just a sum of individual momentum. So we can separate it into separate integrals. This will be dP1, and remember this is a vector. So this is dP1 e to the power minus beta p1 square by 2m integral dP2 e to the power minus beta p2 square by 2m integral dPn e to the power minus beta pn square by 2m. So here's your DIY for today. On the basis of this momentum partition function, if I asked you, what is the average momentum of particle 1, what would it be? Huh?
0,
Why?
because it's an even function.
This thing is an even function, right? So average momentum would be something that looks like integral dP1 P1 e to the power minus beta P1 square by 2m, right? This is even. And when you do it component by component, this is an odd thing, right? So this becomes 0. This is your DIY1 to work through this thing. That average momentum is 0. Average speed is not 0. Your DIY2. And by the way, this is not just true for particle 1. This is true for all particles, right? They are symmetric. The average speed is going to be square root of 8 kTm by pi. Okay, it's just completing the Gaussian, and you will get that. So in this case, you don't have an odd function. P1 is the modulus, right? So it's always positive. So work through these two things. This will give you some, it's a good exercise of making sure that you can still manipulate your partition functions. So I want to go back to equation 4. Equation 4 says that the full particle partition function is integral dPn e to the power minus beta kinetic energy that depends on Pn dQn e to the power minus, no, what did I do? Where did Q come from? drn e to the power minus beta U that depends on Rn, right? This would be true if the particles were if they were distinguishable, right? If I'm trying to describe this thing, water in this bottle, do I really care about the identity of the individual water molecules? I don't, unless one of them is tagged isotopically or something like that. I don't care, right? So this is true for distinguishable particles. But when you're looking at a bunch of molecules in a box, you're doing a biology or a chemistry experiment, or even looking at, you work with Ross Salovich, right? He does atmospheric chemistry, right? You're trying to model something in the higher atmosphere. You're looking at ozone molecules. Do you really care? Oh, that's today ozone number 1 was in a bad mood. You don't think like that, right? It's all just ozone molecules. You have to account for the fact that they are indistinguishable. So here we are going to use what we have done previously, which is our we will assume that we have a classical fluid in low density limit, and this has indistinguishable particles. If this is the case, my Q becomes 1 by n factorial dp to the power n e to the power minus beta k of p to the power n integral drn e to the power minus beta u rn. Okay. Now let's go back to this one and use my formula for the kinetic energy. So
Sorry, I'm a little confused about this. So
Why?
like, I thought that fluids approximately are like, oh wait, this is fluids, not liquids. Never
No.
mind. Sorry.
No, it's liquid too. What's wrong with that?
Well, I guess because like with liquids, they're incompressible. So like, how do you have a low density limit to something where the density is approximately constant?
It's still low. It's still low. I can always say
Maybe
that.
some, like,
The volume in
sense.
which they are is much bigger.
Okay.
They are not packed.
Okay, so like they're small relative to like the space in between.
Exactly. The space is always large, right? In thermodynamics, anytime we try to connect statistical mechanics to thermodynamics, we assume there is a lot of particles and there is even more space.
Okay.
And the ratio is constant, and that ratio is a small number. That's what we are saying here. Okay.
So it would break down for like degenerate matter.
Yeah.
Like the white dwarf. Or,
Yeah. Yeah.
Okay.
Yeah. No astrophysics in this course.
Gotcha.
I'm sorry to disappoint you. So this integral is going to be integral dp1 e to the power minus beta p1 square by 2m, and this is a vector, integral dp2 e to the power minus beta p2 square by 2m, integral dpn e to the power minus beta pn square by 2m. Okay. And that brings me to your third DIY for today. It's the same family. Is to calculate this integral. Here, use spherical coordinates. Why can we use spherical coordinates? Because what is p1 square? That is the radius, right? You already have an integral. What are spherical coordinates? R theta phi, right? And your integrand depends only on r. So you can integrate out theta and phi, right? When you do that, you will be able to show that this whole thing becomes Planck's constant by square root 2 pi mkt whole to the power 3n. Where did Planck's constant come from, all of that? That integrand doesn't have a Planck's constant. Any ideas? I missed something in my equation number 7. Who here really likes quantum mechanics?
H minus 3 to the power n, you have to
I did not divide by h cut to the power 3n here, right? When I count partition function, I have to account that uncertainty principle says that there's a box size limit, right? You cannot get more accurate than that. So this is the poor man's quantum approximation. We divide by n factorial and we divide by h to the power 3n, right? So we account for that and you get this whole thing. So this h to the power 3n is I'm a bad algebra day. Sorry. I blame Pakoda. This thing becomes square root of 2 pi mkt by h to the power 3n, because I had h in the denominator, right? And we give this a name. We call lambda t as h over square root of 2 pi mkt. This is the thermal wavelength. It does not matter that you remember this exact expression. What matters is that when you look at the partition function for a classical fluid, the Hamiltonian, the full energy is separable into kinetic energy and potential energy. Potential energy is messy. We are going to deal with it for our distribution functions and everything. The kinetic energy is analytical. You can integrate it out. You get something that depends on temperature. In fact, higher the temperature, higher is the momentum partition function, right? You have more things to do. That's what we get. So finally, so we are just going to ignore the momentum part of the partition function in what we go next. Sometimes you can use it if you wish, but since it does not depend on position, it's just something that depends on the temperature. If you're going to calculate a property of the system that is temperature dependent, you better not ignore the momentum part of the partition function. You will get an error. So let me write down the full thing. So we have just shown that Q is equal to 1 over n factorial by thermal wavelength to the power 3n integral drn exp of minus beta capital U of Rn, the full n particle partition function. And let's call this as equation number 8. So this is the partition function for a classical fluid with n particles in low density limit. Okay? Any questions about this? I gave you 3 DIY. Please work through them. It will help you stay on top of StatMech. Okay. So this was slight detour to take care of the momentum part. Now I want to come back to equation 2. Equation 2 is the 2-particle distribution function, which specifically accounts for the identity of both particles. Okay. So let's continue with this one.
It's a problem that had like linear momentum. So when you integrate it, so I mean, I could have guessed the form of that by saying like, oh, I can fit these many particles in these many wavelengths, right? Whatever wavelength they have. But if you would have given us like something like linear or non-quadratic, the distribution of momentum doesn't quite give us.
No, it'll be something else.
So what would that be? It would not be thermal wavelength.
It will be something similar to the thermal wavelength. I think for that problem, for example, instead of 3n, I think you had an n. So I would conjecture that it will be thermal wavelength to the power n, but I'm not sure. You will have to work through it. I think it will be similar algebra. It won't be too complicated. You can do it. We won't worry about things like that. We will stay in the normal world. That type of Hamiltonian shows up in a relativistic system, I think. We will stay in good world where momentum is p square over 2m. Everything is nice. Okay. So let me recap equation 2. Equation 2 said that P2, the 2-particle distribution function, is the probability of finding particle 1 at R1 and particle 2 at R2. And this probability is really, if I was to be careful, this is integrating out R3, R4, Rn. It's proportional, it's not equal to e to the power minus beta U of Rn. Why did I write proportional? Because I ignored the partition function in this case, right? The denominator will have a partition function. So if I go to equation 2, I should correct it. This thing is proportional. It's not equal. Okay. Same for this one. It's proportional. It's not equal because there is a denominator which is integrating all of it over all R1, R2, R3, Rn. Dividing by Q. Okay. So I have this. And let me remind you, this is 2-particle distribution function of which is probability of finding particle 1 at R1 and particle 2 at R2. So it has a clear identity of which particle is where. But again, if I go back to my classical fluid, this is indistinguishable atoms. So why do I care about this, right? So I'm going to introduce a new notation. That was a particle distribution function or a distribution function. Now, if I'm interested in, so I am, no, let's be together. We are interested in indistinguishable particles. In that case, I really don't care about probability of finding exactly particle number 1. and exactly particle 2 at 2. I care about finding the probability of finding any two of those n particles at R1 and R2. It could be any one of, it's not just Disha and Divi anymore, it could be any of you all. And furthermore, any of you could be at R1, any of you could be R2. If I swap both of you, I don't care. Which one I pick from you, I don't care. Okay. So we will now talk about non-specific probability of finding any two out of n total particles at R1 and R2. Okay. And this probability is what we call a reduced, it's proportional to a probability. It's a reduced distribution function. So earlier we had distribution function, and now it is reduced distribution function. So the distribution function was P2, where particle 1 is at R1 and particle 2 is at R2. And now what I want to think about, and I'm going to give it a symbol, I'm going to call it rho 2, rho, okay? Same superscript 2, because I'm still thinking about two particles. It's just that there are any two particles, okay? Rho 2, and the variables are the same, R1, R2. But now, it could be any particle. Which one will be higher, rho 2 or P2? Why?
Because you could have any particle in those locations, so you have more ways to have particles.
Does everyone agree with that? And who, apart from Noah, would like to tell me how much higher? Can we write it down approximately at least? Not you. You're done for today. I'll come back to you if there's no. It's a question of how to choose those two particles, right? So how many ways could you have chosen the first particle in? Out of n particles, if you had to pick one particle, how many ways could you have done it in? N. Okay, now I got you. You're Trevor, right? Trevor, how about the second particle? How many ways can I pick that one? N minus 1. So that's my relation. Rho 2 is, and that's why I said it's sort of a probability. It's not kind. You have to be careful about a probability should integrate up to 1 and things like that, right? So I'm being a bit sloppy. But this is how I define my reduced particle, reduced distribution function. Rho 2 is n multiplied by n minus 1 multiplied by P2. Okay? I could do a similar thing for single particle distribution function, right? I could do a single particle reduced distribution function. I don't want to care about finding one specific particle at R1. I want to find the probability of, what is the probability of that finding any of these molecules up here by the cap? Okay, not just all of these, one particular molecule, but any of these molecules, right? So that will be related to P1 of R1. And now it will be only n multiplied by that, right? Because you have picked up any of those particles, any of those n particles. So this is a bit intuitive. Once it clicks, you'll be like, okay, of course it makes sense. But this is a point that students get confused with often.
Is it valid to approximate that factor on P2 as n squared, since n is really big?
Yeah, I will do that at some point.
Okay.
I will do it in a little bit. Yeah, but right now I want to be careful and write it down this way. Okay. N is really large, so who cares about n minus 1? Okay, good question. So I want to calculate the probability of, you are all moving around, and I want, in first case, the probability of finding Ami sitting in this chair. That is P1, capital P, superscript 1. Now I want to calculate the probability of not just Ami sitting in this chair, someone sitting in this chair. Which one will be larger? The second one, because the someone sitting in this chair includes Ami, but it also includes anyone else who might be sitting in this chair, right? That's why it's larger. So it's any two particles. Okay, so it's like it's think about a Venn diagram, right? With this particle, with that particle, and you're thinking about the union of both of them, right? Yeah, and no question is a bad question, by the way. You guys should all ask. Any particle, yeah, exactly. And that's reduced distribution function. And when we think about classical fluids, we are very rarely going to think about P, we are going to think about rho. And we will make further approximations. We are going to think about spherically symmetric fluids. So we won't even care about R1 and R2 separately. Mostly we will care about the difference between R1 and R2 and things like that. So we will make some more approximations. But here is a claim. I'm going to make a claim that for a uniform isotropic fluid, ρ1 of R1 is nothing but the density of that fluid. So that gives us some intuition. That will be sort of our launching point as we go ahead. That if you had a fluid which is uniform, this is not exactly uniform. Gravity is acting, right? Let's imagine this is in space shuttle and this is isotropic and things like that. For something like that, ρ1 would be just the density. Let's try to prove this. To prove this, I will go to equation 10. Equation 10 is ρ1 R1 is equal to N P1 R1. Let's multiply this by dR1 and integrate it out. Okay, so I'm going to do integral dR1 ρ1 R1 is equal to N integral dR1 P1 R1. This is the probability of finding Ami in some position in the room. This chair, that chair, hanging from the ceiling like a bat, I don't know, whatever he wants to do. That has to sum up to 1. It's not going to disintegrate, right? So this thing must be equal to 1. It has to be found somewhere, right? If it is a uniform isotropic fluid, that per construction means that this thing is independent of R1. That is the whole definition of uniform, right? A uniform fluid says the probability of finding any particle does not depend on where you are, right? This becomes ρ1, which does not depend on R1 for uniform isotropic fluid. ρ1 comes outside. It's almost a trivial proof, ρ1 comes outside and we are left with dR1. And on the right side, we have N multiplied by 1, which is N. What is integral dR1? That's the volume of the system. So ρ1 multiplied by V is equal to N, or ρ1 is equal to N by V is equal to rho for a uniform isotropic fluid. For anything else, ρ1 won't be equal to rho. And we are particularly going to be interested in ρ2, the two-particle distribution function. I'm going to show you next that for, so this was claim number 1. Let's go to claim number 2. This thing for uniform isotropic fluid. I'll pause for just a bit. Okay. So the next claim, so we just showed that for uniform isotropic fluid, this abstract thing that you have probably never seen in your life, ρ1 of R1 is nothing but the density rho. Let's go to one further level of abstraction. Now I'm going to talk about ρ2 of R1, R2. The probability of finding any two of these water molecules at position R1 and R2. So what I'm doing here, I fix my origin, I fix a vector R1, which is up here, I fix a vector R2, which is up here, and I'm trying to find out what is the probability of finding any of these Avogadro number of molecules here and here, both at the same time, right? But any of them. So the next claim is that, again, for uniform isotropic fluid, ρ2 of R1, R2 is equal to rho square. For large n. This will be true only for thermodynamic limit. How do I prove this? Again, if I have to prove something, let's start with the definition of what I have, right? So ρ2 R1, R2. What is the definition? This thing is n multiplied by n minus 1 multiplied by P2 of R1, comma, R2, right? This is the definition of the reduced distribution function. So for very large n, I can do what Noah was saying. N minus 1 is approximately n, or one of you said that, right? So this becomes ρ2 R1, R2 is approximately n square P2 R1, R2 for large n. Oh, I need to check something. Maybe I have one more approximation here. One second. Aha, I missed a crucial approximation. Claim 1 was valid for a uniform isotropic fluid with whatever complicated interaction you had inside it. It could be a super fluid, whatever, I don't care. Claim 2, I'm going to put in one more approximation. Otherwise, claim 2 won't work. With no interactions. Okay, otherwise it won't work, what we just wrote down. If there is no interaction, what can I say about P2 R1 and P2 of R1, R2? I have ρ2 of R1, R2 on the left side, and on the right side, I have P2. If there is no interaction, then the probability of finding two particles at R1 and R2 is going to be the probability of is the product of their independent probabilities, right? If there was interaction, then it won't be independent. That's why I had to assume this. So this will be P1 of R1 multiplied by P2 of R2, right? But I'm talking about a uniform isotropic fluid. So why do I care about P1 of R1 and P2 of R2 separately? They are going to be the same thing, squared. Or ρ2 R1, R2 in the limit of this approximation is equal to n P1 of R1 squared. What is n multiplied by P1 of R1? That is equation number 10. That is ρ1 of R1, right? Equation 10 says ρ2 of R1, R2 is therefore equal to ρ1 of R1 whole square.
In the line where you've got the separating the two different probabilities.
From here to here or the next one?
Yeah, that one.
Yeah.
why is it P2 of R2? I thought we were saying P2 is the probability for two particles.
Yeah, so P2 is a function of R1 and R2.
Yeah, so right under it, you have P2 of R2.
Oh, I should be punished. Good spot. Thank you for that. Horrible. I apologize. Yeah. And that's why I kept it to be the same. It's a uniform isotropic fluid. It's the same probability function, right? It's indistinguishable particles and things like that, right? You know, in fact, you don't even need to do. Yeah, if it's indistinguishable, that's going to be the same. That's the idea. So now we have rho 1 R1, and we just showed in the claim 1 that rho 1 of R1 for a uniform isotropic fluid is rho, right? Use equation 11, we get rho 2 of R1 R2 is equal to rho square. And this was our claim for uniform isotropic fluid with no interaction. This seems kind of backward. I said part 3 is all about interacting systems, and there I go, I'm talking about no interactions. But this is going to be our starting point. And Chandler generalizes this. Chandler talks about k particle reduced distribution function, which is going to be rho to the power k in this limit and things like that. We don't care about that, okay? So let's call this, and I'm going to stop in 1 minute, and then I will resume from here next time. So this one is what am I doing? No, don't. I pressed something I should not have pressed. Oh yeah, there we go. Okay, so that's equation 11. I put a blank page by mistake. Let's call this as equation number 12. So so this is a bunch of algebra, which is probably clumsy and makes you uncomfortable. It's a strange way of looking at things. So equation 12 just said that two particle reduced distribution function rho 2 of R1 comma R2, which is the probability of finding any two particles at position R1 and R2, is equal to rho square for uniform isotropic fluid with no interaction, right? Another way of thinking about it is that rho 2 of R1 comma R2 by rho square is equal to 1 for a uniform isotropic fluid with no interaction, right? But in reality, there will be a ton of interactions, and it's not going to be equal to 1. And that brings us to the superhero of interacting systems. And that's where I'm going to stop. For a real system, this is going to be something that is now a function of R1 and R2, right? And that function will be given the name G. G2 of R1, R2, and G2 is known as the decorrelation function. It quantifies how much interaction do you have in your system or not. If G2 was equal to 1, you have a non-interacting system. If G2 is not equal to 1, you have some sort of interaction going on. It could be smaller than 1, it could be larger than 1. Furthermore, we will be interested only in spherically symmetric molecules, really simple stuff. We won't care about G2 of R1 comma R2. Starting next class, we are going to care about G of R, where R is R1 minus R2 divided modulus of this thing. And this G of R is fundamental to a lot of sciences. X-ray diffraction, all sorts of things. In fact, many molecular simulation labs, if you go to them, you will have PhD students running around randomly shouting G of R, G of R. This is the G of R they calculate from simulations. So I'm going to recap this relation between two particle reduced distribution and rho square next time. And then we'll start from G of R. And turns out you can measure G of R from X-ray scattering neutron scattering, all these type of things, something called structure factor. So go through Chandler chapter 7. This is new material. I will recap some of it. It takes time to get accustomed to this material. So see you on Thursday in class.